right, thanks. I would normally wander, but I've been told to not use the lav mic because there's feedback, so I'm going to stand right here at the podium, which is really weird. Very good. I can duck. All right, let's start with a little history lesson. So in 1972, I got to stay close to this, a man named James Anderson was hired by the U.S. Air Force to lead a computer security study. Now, Anderson was a former U.S. Navy gunnery officer. He later became a radio officer. And by the time he had been in this, by the time he was hired by the Air Force, he'd been in the private sector for about 10, 15 years. He was an established expert in computer security, among other things, had a number of patents. The goal of the Air Force study was to determine whether it was possible to create a computing system that would meet the classified security needs of the Military Airlift Command without having to invent a brand new operating system. So that was the goal of the study. So we pulled together this technical team that was a mix of government and academia and industry, and they got together, and about 6 months of work later, they produced this 140-page report called the Computer Security Technology Planning Study. And this paper, you could actually argue, defined the direction of computer security research for the next decade, maybe longer. It enumerated a number of topics for future exploration, and it predicted a lot of software security attack vectors accurately. It got a lot of things wrong in terms of how computing would play out, but it predicted a lot of attack vectors really successfully. And one of the reasons I particularly like this paper and that I'm showing it today is because it contains, to my knowledge, one of the very first technical descriptions of a buffer overflow vulnerability in the historical literature, which I'll show you. So the code performing this function does not check the source and destination addresses properly. This can be used to inject code into the monitor that will permit the user to seize control of the machine. And by monitor here, it doesn't mean the thing that you're looking at in the display. It's this other concept that he raises, which is not important here. But there it is in black and white, in 1972. And software security has been terrible ever since. But that aside, you could also say this was the first of many pieces of computer security research that led us to where we are today in software security. And so that's what we're going to talk about, the state of software security in 2016. Very briefly, this is me. I do application security my whole career, first time at ShmooCon. Hates thought leadership. That's enough about me. Okay, so the stuff I'm going to share with you today is a subset of what my company has published in something called the State of Software Security Report. We do this periodically. We have a lot of data. I'll tell you about that in a minute. And this is our 6th volume. It's designed for CISOs, application security experts, developers, anybody who's doing software and wants a broad view of how software security is going. So the way I describe this report when people are like, well, there's a million reports out there, what is the difference with this one? We report on software vulnerabilities, hopefully, before breaches happen. A lot of the other ones out there that are amazing, the DBAR, other reports, are reporting on breaches after they happen. And so we're trying to talk about what vulnerabilities are showing up in software across the board at scale that may lead to breaches. So why would you listen to me talk about this as opposed to the other hundreds of people that know about software security? The reason is nobody else has application security data at this scale. So this report includes data from over 200,000 application assessments that were done by my company over an 18-month period between the end of 2013 and mid-2015. So we have a lot of customers, we scan a lot of applications. Most of this comes through static analysis, but there's some other analysis methods in there as well. The vast majority of it is through automated means. One thing I should mention as I go through this, I'm going to assume that you have a basic passing knowledge of application security vulnerability, so I'm not going to explain what cross-site scripting is or command injection. And I'm going to expect that you'll just either know or you can Google it later. I'll give you a second. Some might say that this is just as accurate a description of the state of software security today as the very long report that we published, but then that would be a really short presentation. So I enjoy this. Our chief scientist tweeted it, so I thought I would share that. Okay, before we get into it, with any study, I think it's important to know the source of the data, the methodology, so you can frame your interpretation of the data. I don't see this sort of thing covered very often when people are presenting reports, so but I'm going to do it. So I'm going to start by telling you a few of the biases in our approach, and the reason is just to enhance your understanding of what it means. So here we go. So these are some biases that are true of any study of security vulnerabilities, regardless of, the vendor or whatever. We have selection bias. This is our customers. There are people producing software that are not our customers. They have a lot of applications. They may choose 500 of those to analyze and leave out another 1,000. So the data is what we have. And you could think of it as also a best case scenario because we're also looking at data from companies that care enough about application security to actually do something about it. And so there's a lot of them out there that are not doing anything. So again, kind of a best case scenario. Type 1 and type 2 experimental errors. So in automated software vulnerability scanning, you have a thing called false positives and you have a thing called false negatives. A false positive is when you detect something and it's not really real. A false negative is when you fail to detect something that is actually there. And so that's, of course, going to happen, whether it's a manual pen test by a human, whether it's an automated analysis being done by a computer, you're going to have false positives and false negatives. That's expected. That's baked into the data. I didn't really know what to call this, but capabilities bias, we build the technology, we decide what to scan for, we decide where to go deep and shallow in certain areas. We try to, of course, go as deep as we can in all areas, but there's going to be some bias to the nature of the technology itself. So that's also baked in. If we're really, really bad at a particular language because we just released it and we haven't gotten as mature on that as we have for an older language, then that's going to be baked into the data as well. Here's some biases in kind of how you might interpret the data. So metadata omission, I call it. So not knowing the maturity of a particular application may cause you to make some assumptions about, you're kind of grouping it all together. So you're saying like, well, this group over here, which is a really modern dev group, and this one over here, which is legacy, we don't capture that. We don't know how old the application is necessarily. We're lumping all the data together in terms of what we find. And then attribution bias, you see some data, you're like, oh man, this is really, really bad. Like, why is classic ASP so terrible? Those developers must suck. And like, maybe that's true, maybe it's not, but like, that's not in the data set, right? So we have an inclination to do that based on our own experiences and just try and kind of pull yourself out of that and not make those assumptions. Because we don't actually have anything that says that. We can make our best educated guess. Okay, and the last thing in terms of biases, just remember correlation is not causation. Does everybody get this? Okay, so in other words, in case you don't get it, despite what this chart may suggest, you're not going to reduce the number of Nicolas Cage movies by erecting fences around your swimming pools. If you enjoy this and you haven't seen this website that has this graphic and many others, you can Google spurious correlations. There's also a little link to the website in the corner there. But anyway, so just remember, and I'm going to say a few times, remember correlation is not causation. I will say it a few times because you're going to be really tempted to draw some conclusions that are not actually backed by the data. All right, now that we're 10 minutes in. So we're going to start by looking at how different industry verticals compare to one another. So we use industry definitions from the Bureau of Labor Statistics. There's a lot of industries there defined, so we don't necessarily want every chart to have like 50 bars on it. So we consolidate similar industries together. So for example, technology includes technology, telecom, software, electronics, and a few others. So when I show you this, they are based on industry groupings that we didn't make up, but we did make up the groupings to make it simpler to digest. So if you're, say, a financial company, a lot of times what you're going to be asking is like, how am I related to my peers? But we thought it'd be interesting to see how different industries relate how they rank relative to one another. So let's show you a little bit of this. So this shows you which industry does best against standards, and I'll tell you what that means. This is showing what percentage of applications fail an OWASP top 10 policy the first time it's submitted. So first of all, what does it mean to fail a policy in our parlance? That means that you had at least one instance of a vulnerability in that taxonomy. So one SQL injection would be a fail. One cross-site scripting would be a fail. Doesn't matter if you had 100 or one. Vulnerability counting, whether you like it or not, I don't like it. I don't know that you're that much worse off if you have 1,000 SQL injections versus 100, right? So we talk about failing or passing a policy based on if you had anything in that taxonomy. And that's what a lot of customers do too in terms of enforcing policies and compliance. They do a pass-fail sort of thing. And the other thing, which I already said, but I want to point out again, is that this is based on the initial submission only, the first time an application is submitted. And we'll talk about remediation stats kind of later. So, not a lot of variance there. Financial services doing the best, 58% fail. 76% government doing the worst, but that's not a huge variance. And remember, it only takes one vulnerability in the OWASP top 10 to fail, and there's a lot of categories there. This is a slightly different view of the same data, so the failed applications are shown in pink. And again, since the overwhelming majority of enterprise applications are web-based, that's the reason that we're using the OWASP top 10 in this case as a standard to measure against. So again, we have a clear best and a worst. We've got the financial services as the best, government is the worst, and the remaining sectors are kind of grouped pretty closely in the middle. And remember, this is not just like, 5 or 10 applications in each industry. There's a total of 200,000 applications here. In case you didn't notice, and you probably did, even the best performing sector is failing for 3 out of 5 applications. This is really awful. Okay, show of hands, who thinks flaw density, and if you don't know that term, flaws per megabyte, flaws per 1,000 lines of code, something like flaws per some unit. Who thinks that is a valuable thing to measure? It's not a trick question. All right, so like 10%, maybe 15% of the room. So both answers are sort of correct, but there's a lot I want to say about this, and our customers asked about this, analysts asked about this. They really want to know flaws per megabyte, which is in fact something you can measure, but it's a very misleading metric because the programming language itself has a really significant impact on that number. Some language you can accomplish a lot of stuff in very little code. Some of you may have seen this comic. I know it's trendy to be an XKCD hater, so if you're one of those, go ahead and grumble to yourselves while everybody else reads it. The point is, this guy's flying. He's like, how are you doing that? Python. Oh, how did you do that? Import anti-gravity. And it would probably take at least 1,000 or 5,000 lines of code to implement anti-gravity in Java. So there's a variance in the density of what you can do in a particular language, and that's why flaw density is kind of a bogus number when you use it in certain situations. But here it is anyway. Some languages, particularly C and C++, produce compiled code that's much higher density than others, like Java, which means that an industry or an organization that has a higher prevalence of those denser languages is going to have an overall flaw density that's higher as well. Just math, right? So I'm giving you these industry comparison charts, and I'm immediately telling you not to read too much into them. Like manufacturing, which is on the very left there, it's very high. It's 352, what's the flaws per megabyte? And healthcare is really low. Does that mean that manufacturing companies write really, really bad code? I mean, maybe they do, but probably not 23 times worse than healthcare. It's probably, my laptop is sliding off the table. There's probably more about what's making up those numbers, what's making up that application portfolio. So where flaw density can be a useful metric is to track internally with an organization or for an application over time. So where you have one thing, and you're seeing, is it getting better or worse? Not comparing completely different populations. So it is useful for benchmarking that progress as a company, as a dev team, as a business unit. So we'll come back to this metric again later when we talk about remediation rates, and we'll look at it within that frame. This is about as small as the bars get. This one's a little bit for the screen size. But what we're showing here is the prevalence of a few different vulnerability categories that we've chosen in different industry verticals. So SQL injection and cross-site scripting have consistently been at the top of the list for application security flaws. Cryptographic flaws are in there because they've been highlighted in recent years as results of major vulnerabilities like Heartbleed, or just, we're all concerned about security and privacy now, so crypto stuff is pretty hot. When we look at the prevalence of SQL injection and cross-site scripting across the different industries, we see a fairly similar level. You do see some bars kind of stretching out to the right, so government stands out as being significantly worse than other industries in that regard. Those numbers are anything to go on. The recent, not so recent anymore, disclosure at OPM may not be the last significant event in U.S. government security. Crypto issues are a slightly more confusing picture. You've got this cluster of prevalence around 60%, and again, that 60% of applications having at least one cryptographic issue, so prevalence again. Healthcare stands out there as having extremely high prevalence in that category. Manufacturing and, what's the color there? Government are a little bit lower in that category. So, again, we have a lot more of this in the report itself. I'm not going to kind of read to you what the percentages is for each one, but it is interesting to see that variation where different industries are doing very well in some areas and very poorly in others. I shouldn't say very well. They're doing better. So another slice, like you have all this data, you can slice it any number of different ways, and we try to do it not entirely differently each time we do a report, but we try to do a few things that are different and keep a few things the same for consistency. So one thing you can do is you can slice the data by language. So we'll compare different programming languages now and looking at the relative security of applications written in those languages and how prevalent certain flaw categories are. So remember what I said at the beginning about missing data. We have to be careful not to draw too many conclusions based on this. So first of all, the population. This shows the language distribution across the entire data set for our past 3 reports. And remember, the selection bias is a factor, but there's still a pretty sizable increase in .NET usage, which is that kind of dark pink color. Even when you account for the fact that over time, we've had a broader set of supported languages that we take in. .NET is actually increasing quite a bit. That's really the only thing you should take from that chart, is that .NET appears to be on the rise relative to Java in enterprise environments, because most of what we do is enterprise. Now, if you go back about 10 slides, you'll remember we talked about comparing industries on OWASP Top 10, so we're doing that again here, except sliced by programming language instead of by industry. So unsurprisingly, compiled application languages like C++, Objective-C, that are not typically used for creating web apps have a higher OWASP pass rate. That makes sense, right? Fewer web vulnerabilities in non-web apps. Okay. General purpose bytecode languages like Java and .NET, which is the highest volume of applications, are a little bit lower. And then scripting languages like classic ASP, PHP, Cold Fusion are coming in at the bottom there, a far lower pass rate. So what conclusions can you draw from this? Java and .NET are close enough that I would just consider them equivalent. Scripting languages clearly need help. There's something going on there. We have, you can make some guesses about that. Prevalence, again, of certain types of vulnerabilities except sliced by language instead of industry. So, again, as you would expect, SQL injection, cross-site scripting are far more prevalent in web scripting languages. Classic ASP, Cold Fusion, and PHP compared to .NET and Java. And, my guess about this, and you can make your own guesses, my guess is that it's related to feature sets within the language. So .NET and Java have a lot of defenses built in. I mean, think about the evolution of cross-site scripting defenses in the .NET framework over the years. It's gotten pretty good. You compare that to PHP, where I think it wasn't even until PHP 5, maybe 4, but I think PHP 5, where you could even like bound parameters and database queries was actually part of the core. Classic ASP, what sort of security APIs does it have, if any? Right. So developers are working within this framework that doesn't give them many opportunities to protect their code. Again, that's just a guess. Cold Fusion has actually gotten better over the years, and we take a lot of flack every time we publish results that show Cold Fusion has a high prevalence rate. I mean, we're just going based on the data we see. It actually is high. But we'll get feedback from developers saying, well, Cold Fusion is not as bad as you think, like it's getting a lot better. And to some degree that's true, it's improved. For example, they incorporate the eSAPI library from OWASP into the Cold Fusion distribution now. That being said, the best library for cross-site scripting defense from OWASP is the OWASP Java encoder, and they haven't caught up and packaged that instead. So it is a little bit behind. It is getting better. Other languages that are sort of dead or legacy are not getting better, right? You're not getting new classic ASP defense libraries anytime soon. I also want to call out the high rate of command injection in PHP. So that's the little green bar way out to the right in command injection. I'm calling this out because we got challenged by a few people on Twitter about this. And the general comment was like, well, I audit PHP code all the time, and I never see that. Nobody ever shells out and does a direct command in PHP. I never see this. There's no possible way it could be at 35% or whatever that bar says. And so the first thing is, it's not just OS command injection in that category. It's OS command injection, it's argument injection, so CW 78 and 88 are kind of included in there. And also, we actually do see PHP apps shelling out using user input. They do that. This is where the kind of your experience comes into play. If you're a pen tester and you're doing code reviews or pen testing of PHP applications, once a week, one app per week or one app every couple of weeks, you're probably getting the most critical, most scrutinized applications that the company has, the most important ones. And so, yeah, of course, they're probably going to be overall a little bit better than the ones that are kind of further down the priority level. Like, we're looking at all of things. A lot of times we'll be dealing with companies that have hundreds or thousands of applications. So we're getting the really good stuff and the really legacy stuff. And that's going to bring those averages up in terms of what types of vulnerabilities we're finding. So the data actually stands up when you look at it with that scrutiny, and the person who made that comment, his experience is also correct. So he's like, I never see that. It's like, well, we could show you. We always get asked which language is most secure, and such a loaded question. And this slide shows, it's a little busy, but this slide shows there's no simple answer to that question. So let's look at manufacturing, which is right there in the middle. So they're a little bit different in terms of language makeup. So they're kind of bucking the trend of this whole Java.NET dominance thing. They have a lot more native code, C++, and yet they're also highly ranked in terms of security quality. So the numbers over on the right are the rankings. If you go way back to the beginning where we said which industry was doing the best, so remember financial services was on top and government was at the bottom, so that's on the right is their rankings. So even though manufacturing has more native code languages than other industries, they're actually still doing better from policy compliance. So, I think it has a lot to do with how seriously the industry takes security, how much it's baked in the dev life cycle, but again, this is just a guess. It's not surprising to me that financial services is at the top. Having worked with financial services companies my whole career, they're always a little bit further ahead in terms of their thinking, their adoption of tools, their adoption of process. Not all of them, but what I see here is that if there are any inherent security differences in language choice, I think a lot of it can be overcome by process and programs and so on, taking it seriously, building workflow around it. So this is my conclusion. Program maturity probably has a greater impact on security quality than language choice. I mean, again, you think about manufacturing, they've been dealing with things like process and supply chain and thinking about where, parts come from. So if you apply those same disciplines to software, which they do, and we see that, we're like, wow, you guys are thinking about this much more forward thinking than a lot of other companies that are not thinking of supply chain and things of that nature. Yeah, you guys have a really rigorous workflow around how you deal with parts or how you deal with, manufacturing process. And so maybe it's a mindset issue. I don't know. This is about as deep into the data I'll go, and I call this out, it's very, very specific, cryptographic flaws in mobile apps. And that's just because, again, this increased scrutiny recently on privacy and security, especially around mobile. I want to call it specific CWE categories that we found in Android and iOS applications. So I'm less concerned about the top one, 331, insufficient entropy, that gets flagged when you use a random number generator that's not sufficiently random. And that's fine. I mean, not all the time, but most of the times they're using those random numbers for something that's not security critical anyway. So not as big of a deal in most cases. But then the next one down, 297, is a huge concern because improper validation of certificates. And all the time you look at mobile applications and they've disabled that check. So what does that mean? Well, you got man in the middle there, right? You're getting a certificate, the math works out, you have encryption, but you're not validating the identity. And for some reason, mobile apps are doing this all the time. Not been able to get to the bottom of why. I think anecdotally, you talk to developers about it and they're like, oh crap, I turned that off because QA. And then we didn't want to cut a certificate just to make it work in QA, so we turn it off. You have to actually write code to override that check. It's not as usually just true false sort of thing. You actually in Android have to write a class that overrides the certificate validation, and you have to really shoot yourself in the foot. So in a number of cases, anecdotally, they turn it off for QA purposes, and then they just forget to turn it back on. Anyway, we see that a lot, and that's really troubling. And the reason for it, the root cause, not just the fact that QA is, I think the root cause is developer maturity, but obviously I don't know for sure. But you have a lot of mobile apps being developed by people that have not had as much experience coding, and that's not to say that people fresh out of college can't do a good job, but I don't know, it's baffling that it's that high, and it's consistently that high over numerous reports. Pretty crazy. Okay, you guys are doing well, but wake up. This is a lot of pretty dense material, so I'm going to, this is a first for me. I'm going to reward you with a few pictures of cats from the internet in various stages of co-development. So feel free to voice your approval or disapproval, and then we'll do a few more charts. So this cat appears to be working on some sort of fluid dynamics simulation, very complex. This cat is, contemplating a change to his algorithm. Maybe his code's compiling. I don't know. This cat is just getting started in coding, but he's already realizing that C++ may not be the best option these days. Okay, that's all. So back to it. More charts. More charts. So we've talked a lot about languages and vulnerabilities and industries and how different organizations compare with one another, but that's really only half the picture, because I love this quote. I can't remember where it came from, but anyway, you can't scan yourself secure. You can scan all you want, but if you don't fix stuff, what's the point? If you got the fewest flaws out of the gate, and the other company is actually fixing their stuff. So you actually have to look at remediation. How are companies, organizations, industries doing at fixing the stuff that they actually find? Something I'm really proud of, just as a person that's worked for this company for a long time, across all of our customers in 2015, we detected nearly 10 million flaws, and customers have remediated nearly 7 million of those. And that's just last year, which is pretty cool. Okay, so which industry fixes the most vulnerabilities? Are you surprised? So much bigger variance. Manufacturing, I mean, I was surprised the first time I saw it. Maybe it's not as shocking as I think. So we'll get to this. So this is an uglier view of the same data, but you can see there's this huge disparity. When we went back to how the industries did in terms of initial submission, there was that very narrow spread, right? They were all between like 60% and whatever, 80%. But here we've got government only fixing 27% of what's found, and manufacturing is way up there at 81%. So again, a lot of factors may be at work there. There may be regulatory drivers contributing to that fix rate. There may be, again, I said about manufacturing, that process improvement methodology that they kind of have baked into their culture. They may also be better at rolling out policies that are that the developers view as achievable. So imagine you have a scenario where like you're scanning an application, you find thousands of flaws, and you say to your developers, like, you have to fix all these within the next month. Like, they're going to come back and either laugh at you or they're just going to not do it because it doesn't seem achievable. And what we found in dealing with lots of enterprises that are trying to roll out policies on a wide scale like that is that you have to make things achievable. And so maybe the first time around you'd say, well, you have to fix all the very highs and highs within 90 days. And that seems ludicrous to people that have done pen testing or that understand how quickly these things can actually be fixed. But we have seen a lot of companies have success doing that. And then they make that step, and then they tighten the policies. But if off the, right out of the gate, you're like, well, you have to fix everything immediately, then you've actually created the situation where nothing gets done because it just seems insurmountable. Again, I do know there are cases where companies have had success because they do that. I don't know if that's the reason that 81% and 20 or 27% are, there's that disparity there. But I think there's probably some contribution of things like that. So remember I said we'd come back to flaw density. So in looking at how flaw density changes from the first assessment to the last assessment of a particular application, that's useful. So in blue we're looking at all flaws, and in green we're looking at only very high and high severity flaws. And applications that are only assessed one time, which is not represented on this chart, but have not had any remediation in the time frame, the window of the study. You see about 153 flaws per megabyte. So the ones that actually are getting remediated are lower. So over time, you see that customers reduce flaw density for all flaws by going from 58 to 50, but for the flaws that are ranked severity high and very high are going down much more drastically. And what this suggests to us is that customers, this should be a shocker, customers prioritize remediation of the high and very high severity flaws over fixing other ones. And it almost suggests that their security policies may focus exclusively on those flaws. In other words, they may be intentionally ignoring remediation of those things that they view as less severe. Again, that probably makes sense logically, but I have the data to back it up. Okay, now we get even dicier. So remember, correlation is not causation. So one of the things we make available to customers is like a readout call, and you get on the phone with somebody who knows security and development, and they walk you through what we found and kind of how to fix stuff, and you can ask questions. And it's not required, but we get a lot of good feedback on the experience, and so we do that for a lot of organizations, especially the first time through. Excuse me. So you'd expect that that would have a positive impact on remediation rates, but you never know until you measure it. So what we did was we looked at applications where there was a readout versus application where there wasn't a readout. And we looked at the percent decrease in flaw density for that particular application. So again, comparing point A to point B timeline-wise for a particular application. So flaw density is fine there. And we saw a significant difference. Applications that did have remediation done, but without a readout, reduced their flaw density by 17%. And the applications that rescanned, fixed some stuff with a readout, was 42% reduction. So that's 2.5 times better when there was a readout. Was it because of the readout? I don't know. Did they do the readout because they're just really they're more attuned to application security and somebody's kind of like cracking the whip? Maybe. I like to think it's because of the readout, but I can't tell you that for sure. But there's definitely a correlation. I mean, the numbers are pretty stunning. Another thing that we sell to people is kind of CBT-based e-learning around application security, secure coding, and various things of that nature. So we thought it'd be interesting to try and measure the impact of e-learning on remediation rates. But that's even harder to connect the dots because there's a lot of other factors, and you would think that the more likely outcome of e-learning, if there was a positive impact, would be there's just fewer flaws in the first place. When you look at the overall fix rate of customers who have established an e-learning program, we notice that the fix rate is considerably higher, 75% vulnerabilities fixed versus 58, so it's a 30% difference. And so it does suggest there's some correlation with having that type of program around compared to your fix rate. But there are all these other things that are in play. Having a program doesn't mean that the particular developer for that application took that course. We're not weighing in how well they did in the course. We're not factoring in AppSec programming maturity. We're not factoring in regulatory compliance drivers. We're not factoring in the remediation coaching that we factored in on the last slide. So it's really hard to take one single factor and draw a conclusion about it. And that's why I put this. This is a really contentious topic, and some people really scream at you when you say that security training could possibly result in more secure software. So I think it helps. Personally, I think it helps. I've got a little bit of a correlation there between companies that have a program and those that don't, and the ones that have a program have a higher fix rate, but I don't have any way of proving that, so I did not make that claim. And this is the last one. To wring every last bit out of the data set, we decided to see if there was any variation in fix rate based on the type of analysis performed, so static analysis, dynamic analysis, manual penetration testing. And we saw that, on average, companies tend to fix vulnerabilities at a higher rate when it's a static analysis. There's a number of reasons for that, I think. Static provides a little bit higher fidelity results around root cause, so when you can narrow down a finding to a particular file and line of code, it points the developer exactly where they need to make a fix. Whereas if you're doing like a web scan, a dynamic scan, you're going to get a URL, and you're going to get, here's what happened when we sent a request and response, and here's what we saw, but you're not going to necessarily give the developer the exact line of code. Now, a lot of them are going to be able to figure out, obviously, it's their application, they kind of know how it works. But when you can give somebody very prescriptive guidance about where to go and what to do, it's even easier. So that's my best guess about why you see that variation between static and the other two types. If you think about a manual pen test, you're getting kind of the same level of information that you are for a dynamic scan, right? You're getting a URL, you're getting a request response, you're just getting maybe, well, we injected something into this particular parameter. But again, they have to go and figure out, all right, where does that map in the framework I'm using? Where would I actually put validation, and so on. This last section isn't directly related to our study, but it's something I wanted to include anyway because I always feel we're doing presentations without putting some sort of actionable thing at the end to kind of take away. I mean, you can all go read the report, but we run programs for a lot of companies, and if you look at kind of what makes them successful, there's some pretty basic things that you can do to kind of, I guess, raise your chance of success. So I want to give a few tips in case you're one of the people that's responsible for software security at your company going back. So one more quick story. Around the time of World War I, only 7% of American households owned toothpaste. And the Army had enacted the draft around this time, and they were finding that so many recruits were coming in and joining the Army, and they were showing up with rotten teeth, that government officials actually declared poor dental hygiene a national security risk. This is true. Around the same time, a man named Claude Hopkins was hired by Pepsodent, the toothpaste company, to design a national ad campaign. And Hopkins was this marketing genius who had done these various campaigns in the past with great success. He'd done this Palmolive campaign, which got a huge uptick in Palmolive sales, and the ads claimed that like Cleopatra had used Palmolive, which is completely false, obviously. But he was like this marketing genius. Anyway, so he needed to find something that would make people want to brush their teeth more often so that you could sell more Pepsodent. And so he went and started reading dental literature, and dental studies and dental textbooks, and he seized upon this thing called mucin plaques, and it's just something that accumulates on the teeth over time, naturally. And he's like, so he renamed that to the film or the dirty film, the yellow film. And what he did is he kind of appealed to the public's narcissism or desire for beauty, and he reframed Pepsodent as not a healthcare thing, but a beauty aid, which was brilliant. And so what this did was, to get people thinking about it in a different way. 3 weeks after the ads went national, Pepsodent couldn't handle the demand. 3 years later, it was an international product. 10 years later, 65% of American households owned a tube of toothpaste. Still not a really high number if you think about it today, but 65 from 7 is pretty good. And so what he did is he defined, and I don't know if he was doing this, he was thinking about it in this way, but he defined a simple cue, the film that would develop on your teeth every morning, and that would trigger a particular behavior, which was the brushing, and then there was a clear reward associated with that, which was, being prettier. And that cycle created this habit. And at the end of World War II, the military downgraded poor dental hygiene, where it was no longer a national security risk. Now, that's a great marketing success story, but what does that have to do with AppSec? I think we have to think like Claude Hopkins in terms of motivating developers to build habits around security activities, whether that's scanning their code base after every build, or whether it's remembering to follow a security checklist every time they build a new feature. Whatever. Creating a habit can be extremely useful. You can imagine how a daily task that they'd have to do every day or with every feature might be more useful than a quote-unquote habit that's like do a pen test every year, because you do it and then you forget about it. It doesn't really change your behavior. So there's not really a one-size-fits-all approach here. It depends a lot on how development is done in your company, what type of culture you have. But if you can find a corresponding trigger and drive the particular behavior that you're trying to drive, and hopefully there's some reward towards that, you're most of the way towards creating a habit. If you want to read more about the Pepsodent thing and other, sort of the psychology of habits, there's a really good book called The Power of Habit that gets into that a lot more detail. I would recommend that. So number one, find ways to create habits. Number two, I talked about this earlier, but the fact that when developers receive remediation guidance, they did better remediation. The point is that they did remediation. So again, if you're only focused on how much you can scan as opposed to how much you're fixing, then you're kind of focusing on only half of the problem. So how do you make that push towards remediation-focused program? Any number of ways. You could mandate a readout. You could do something simple like making sure that you import all your findings into the bug tracking system, because what do developers do every day? They go to the bug tracking system and they fix the quality bugs that came up, and there's definitely a habit there, right? So they've got, if you think about queue behavior reward, you've got the queue, which is like checking Jira or Bugzilla, the behavior, which is fixing bugs, and then the reward is like being able to mark tickets as closed, which you may not think is a reward, but like trust me, developers love to mark tickets as closed. So number two is just thinking about steps that you can take to encourage and facilitate remediation. And again, that seems very obvious, but again, if you go back to the data where we showed that how much stuff was not getting remediated, it's obviously not a solved problem. The third thing, Peter Drucker, if you don't know, is kind of sometimes given credit for modern management philosophy. And anyway, he said what gets measured gets managed. The idea is pretty simple here. Something that you're paying attention to and actually managing will cause you to improve in most cases. Unless you're like actively sabotaging the process, you will probably get better. And it's sometimes hard when you're really close to a situation to see progress subjectively, just like, you have your kids and suddenly they're like really tall, or like, one night they're 8 and the next night they're 12. Like you don't see minor progress subjectively unless you're measuring. And so if you measure stuff, whatever it is, remediation rates, flaw density, whatever it is, you're able to kind of give yourself credit for what you've done, and you're able to track and manage progress over longer periods of time. So number three is measure early and often. Again, this seems so cliche and obvious, but many programs do not do this very well. So I'll give you those three things. Form habits, focus on remediation, create metrics. So there's my takeaway. So that's all I have for you today. I have 5 minutes, I think, and I'd be happy to take a few questions. There. Yep.
Are there fewer faults that are fixed more quickly on the financial side of the house?
Yeah. So have we looked at flaw and fix rates and comparing different types of applications that handle different sorts of data, like financial data versus healthcare data? The answer is, beyond looking at those industry slices, no, because most of the time when we're doing an analysis of an application, they're uploading us compiled binaries, and we don't really have the context of the application. We know that it comes from a healthcare company, but maybe it's like, maybe it's not actually dealing with PII, right? Maybe the financial one has to do with, something that's that doesn't have that sort of data in it, but it's related, maybe it's trading or something like that. So we don't have enough metadata around what the application is being used for and its context to really make that slice. So we go as granular as we can, but with the industry. In the back?
So you talk about developers or QA people turning off TLS during QA because certificates are expensive. What would your response to that be? I mean, wildcard certs aren't that expensive, and with things like Let's Encrypt, there's really no reason to do that anymore.
Yeah, the question is, so with mobile apps and the whole certificate issue, certificates are actually cheap, and why would people do that? Yeah, I agree with you. When I said expensive, if I actually use that word, I think I was not using expensive in the dollar amount, but more just in the hassle amount that they have to cut the cert and put it in the QA, and then a lot of times the QA servers have different names, and then, so it's more of I think a hassle thing. But, you're right, certs increasingly now are low cost or free, and I totally agree with you. I don't get it. Yes, right there.
To what extent do you think the number of flaw remediation for government is skewed with the time it takes to remediate?
So to what extent do I think the remediation numbers for government are skewed by, the amount of time that it takes for them to remediate? Well, so this study was an 18-month window. So if they scan an app at the beginning of that window and had fixed it by the end of the window, it was included in remediation. Now, you do have cases where if something was scanned for the first time near the end of that window, it wouldn't be, and maybe they fixed it like a day after we closed, the window ended. They wouldn't get credit for fixing that because both the beginning and the end didn't fall into that. So I think probably with any industry, there's some of those cases where you span that border of when we started or ended the window, but 81% versus 27% is pretty wide. So yes, it's probably a factor, but it probably only explains like a really small amount of it. It's just a guess. Yeah, right in the front.
On your language list, I didn't notice some what I consider common languages for web application frameworks, so Python or
Yep.
Ruby. Are they so good they're not on your list, or what?
So the question was about languages that were not included on the list of language comparisons, such as Python and other languages. Remember we talked about selection bias? So it's things that we support. So we do, for example, we do support Ruby on Rails, but we just don't get a lot of it from customers. It's not as prevalent, at least in enterprise environments, so we just don't have as much data on it. Python's coming out soon, but of course, since this was going back to 2013, we just didn't have any data on it. So yeah, that's why I kind of call out, like, remember the selection biases are, what features we build, what things we support, and, what our customers choose to give us. Yeah, right here in front.
So you've been talking a lot about flaws. Static analysis tools generate warnings. Some of those warnings actually correspond to coding mistakes. Some of those coding mistakes actually lead to exploits. So when you say flaw, do you mean warning or do you mean actual coding mistake?
So the question is around static analysis. When I use the word flaws, what percentage of those are actually exploitable flaws? I'm going to paraphrase. That's just the terminology we use. If you want to use warnings to mean the output of static analysis, that's fine. Some tools may use that.
When you use flaw, what do you mean?
What I mean is the direct output of what we provided the customers. Some of those will become exploitable. Some will not become exploitable. That's true across the board. So that's part of that's part of what I was talking about with experimental error. Right there.
So your flaw density graph for the remediation, you had the very high and high severity flaws go from 19 per megabyte to 8. You had overall from 58 to 50. So you have a larger drop in the very high and high density ones than you have an overall drop. So does that mean that you're seeing increased lower severity flaws as a result of the remediation?
So with, trying to paraphrase that one. So with very high and high severity flaws density reducing from 19 to 7 or 19 to 8 or whatever, does that mean there's an increase in the lower and medium severity flaws? I would say not a statistically important increase. I mean, there's always fluctuation, right? You write new code, you scan again, you introduce some new flaws. But what it's just really telling us is that people focus on the higher severity flaws first, which is what you would kind of expect them to do, but just the data kind of plays that out. We're not seeing like significant increases in medium severity because they're focusing on very highs and highs. We're just seeing them fix those on average slower and, you know, with less, I guess, intensity than they fix the very highs and highs. Oh, I have a stop sign. So I'll be around. Thanks for coming, and enjoy the rest of the conference.